just as a review of what we went over last class, here we have a queuing system. And so processes, this circle in the middle is going to represent the processor. And this queue is going to represent processes that are in the ready state, waiting to get on the processor to start running. If a process starts to run, and then maybe after the operating system decides that a time quantum is hit, it could take it off the processor and then put it back on the end of the queue. So this picture kind of implies a first come, first served queuing discipline in this case, but if the operating system wanted to, it could start shuffling these around based on a priority. So you might get shuffled to the front or the middle, or if you're near the front, you might get shuffled to the back. That's an option the operating system can do. So you could run for a while, and then you could time out and then go back into the queue. You could also run for a while and then ask for some resource that might not be available at the moment. If you ask for a resource that's not available, and these resources could be many things. It could be semaphores that programmers have created to use to talk to each other. It could be a disk drive. You could have multiple disk drives. So in this example, just to show we could have more than one thing, we have 2 disk drives. So let's say the only resources on this system are the processor, disk drive 1, and disk drive 2. And let's say we have performance monitoring running on our operating system. So we can keep track of when the process state changes from running to wherever. It could be blocked, it could finish, go into the zombie state on its way out. It could go to a disk drive. So our performance monitoring thread can keep track of this stuff. So we could keep statistics like what percentage of the time does a process hit the processor and then go to disk drive 1? What percentage of the time does it go to disk drive 2? What percentage of the time does it time out and go back into the queues to let some other process run? What percentage of the time does it visit the processor, and that's its last visit, and it finishes and leaves our system? So we could keep all those statistics, and then we can shuffle the resources around or allow processes to have more pages or less pages if it's page faulting too much, to change these numbers to make the numbers better for our performance. So I think what we talked about last class was if we notice that this is our overall queuing system, a process comes into this queue, and it may bounce to other queues or may bounce back to the same queue. We decided that to figure out how much time a process takes from when it enters our system until it leaves our system, which last class we referred to as the response time, we needed to calculate. Does anybody remember, or anyone who wasn't here last class want to just take a guess? If we wanted to calculate how long it takes from when we come into the system until we leave the system, if it hits this queue a certain number of times, it hits this queue a certain number of times, it hits this queue a certain number of times, how would we calculate the total amount of time until we finished? Okay, so what we'd want to do is we'd want to calculate how much time does it take to visit the queue, times how much time do we spend at the queue, and then add it all up for all queues. Okay, so where we left off last class was we were able to calculate how many times we visited each queue, but when we got there, how much time did we spend there? We didn't know that because, and what do we have to know to figure out how much time we will spend at a queue? We'd have to know how many processes are in front of us, how long each one of those takes to finish, and then how long will it take for us to finish? And that's how long it would take, assuming it's a first come, first served queue. It's different if it's a priority queue. So, to get to the idea of when we arrive at a queue, how much stuff do we expect to see in front of us? So, if you arrive at a queue, and we'll follow the MM1 example, the MM1 queue we talked about last class. and we arrive at an MM1 queue, where we want to know how much stuff is in front of us, figure out how long does that take to get through the system, and then we have to get through the system. And that'll be how much time it takes for a visit to the queuing system. So we're going to model this using states. We're going to say state 0 is the probability or the state of us arriving at a completely empty queue. So nothing is on the server and nothing is in the queue. When we arrive, we go straight to the server and we get served and then we leave. So we'll call that state 0, the probability that nothing is in the queue. State 1 will be the state where there is actually one customer in the queuing system, which would mean that customer is being served. So the queue would be empty and the server would be in use. If we go to state 2, that means when we arrive, we notice that there are two processes in front of us. One being served, one in the queue, and then we would be adding ourselves to the queue. So state 2 is two processes in the system, one in the server, one in the queue. State 3 would be one in the server, two in the queue, and a total of 3 in the whole queuing system when we arrive. So that being the case, here's an interesting question. Let me pose this question and see what you think of this. The number of times over a given period of time, let's say the number of times over a day, that we go from state 1 to state 2 would be equal to what in relation to going from state 2 to state 1? So I just want to try to get some intuition going. Anyone just have a guess for that? Well, let me ask this question. Suppose you're in a building that has an elevator, and the elevator is going up and down all day long. And you're asked the question, how many times does it go from the 11th floor to the 12th floor? Doesn't mean it has to stop at the 11th floor. It could be going like 9, 10, 11, 12, 13, 14, 15. But it passed from the 11th floor to the 12th floor. Let's say that happens 50 times a day. How many times did it go from the 12th floor to the 11th floor? Does that make sense? Well, that's an important part of the intuition for what we're doing here. So, if it went from the 11th to the 12th 50 times in a day, how many times did it go from 12 to 11? 50, right, because it can't go up 4 times and come down once. Every time it went up, it had to come down exactly 1 time.
Well, would there be floors above the 50th floor though, or are we assuming that there's no other floors?
But if there are more floors above it, if it's going up there, that's fine. I'm just saying it went from 11 to 12.
Okay.
At some point, like let's say it started at the first floor, as the day goes on, if it went 50 times from 11 to 12, then it must have gone 50 times from 12 to 11.
Yeah.
Assuming at the end of the day it's below 11. It could have been 49 and it's still up there. But it's it would be, the number of times you go from one state to the next one has to equal the number of times you went from that state back to the previous one. So that's a very important part. What our goal here in analyzing this queuing system this way is, we want to figure out, our goal is to figure out when we arrive at a queue, on average, what's in front of us. Well, if we know the percentage of time there's nothing there, plus the percentage of time there's one customer there, plus the percentage of time 2 and 3 and 4 and so on, we could add up all those percentages and take an average. So that's what our goal is. We want to figure out what percentage of the time are we in every one of these states, and then we'll average them all out. So, some thoughts on, we're going to call this topic birth-death processes. So basically, if there's a society that has people being born, every time someone's born, the population goes up by 1. Every time somebody dies, the population goes down by 1, and the state just keeps changing. The state is that number. So here's some thoughts on birth-death processes. Okay, the rate of moving from state 2 into state 3 should be the same as the rate of moving from state 3 into state 2. So the rate meaning how often it happens every time, how many times how often it happens over a period of time should be the same. So for example, over the course of a day, the queuing system moves from state 2 to state 3 5,000 times per day, then the rate at which the system goes from state 3 to state 2 should be 5,000 times a day, except that one case where it could be 499 because we went from, we were starting at 0, we went up, and then, but we didn't come down one last time. But they should be approximately equal. So then, that being true, this is a very important part of our intuition. The probability of being in a certain state I, meaning how many customers are in the system, the probability of being in state I and going to I plus 1, going to the next highest one, should be equal to the probability of being in the higher state and coming back to the previous state. So the probability of being in any state I and then having a death, meaning the count drop by 1, should be equal to the probability of being in the lower state and having a birth. So that's the property of the birth-death process. So we talked about last class, we said we're going to use lambda to be the rate of which stuff enters our system, and mu to be the rate that stuff finishes and leaves our system. So the probability of being in state, any state, I plus 1, times the probability of a death, which would be mu, should be equal to the probability of being in state I and having a lambda. So if we multiply this by lambda and divided this, multiplied this by u, this by mu, this equation should hold. So we can take that concept and then just say, okay, our goal now is to try to figure out what is the probability or the percentage of time we're in each one of the states, 0, 1, 2, 3, all the way off to infinity, and then take an average. And then we'll know on average when we arrive what's in front of us. So the probability of being in state 1, if this mu was written up here, so it would be lambda times probability of being in state 0. If we're in state 0 times the rate at which we go to 1, should equal the probability that we're in state 1 times the rate at which we go to 0. It's kind of like saying the elevator is on floor 0, try to imagine a floor 0, and goes up at a certain rate, and the probability of it being on the first floor and coming down at the same rate should equal each other. So the probability of being in state 1 is mu over lambda times the probability of being in state 0. Okay. If that's the case, the relationship between state 2 and state 1 should hold. The same relationship. It should be lambda over mu times the probability of being in state 1. So the probability of being in state 2 is lambda over mu times the probability of being in state 1. And considering that we can substitute this for probability of being in state 1, we can end up saying that the probability of being in state 2, we can connect it now to state 0. So it'd be lambda over mu times lambda over mu times state 0. So maybe a concrete example might help here. Let's say we could figure out the probability of being in state 0 is 50% of the time. And lambda over mu is, let's say, 1 divided by 2. So if 50% of the time this system is empty, then 25% of the time, half of a half, 25% of the time we're in state 1, and then half of that, 12.5% of the time we're in state 2, and 6.25% of the time we're in state 3, and so on. So we can now figure out the probability of being in all the states if we can just figure out the probability that the system is empty, because every one of these numbers is connected to the system being empty. Actually, for any state, the probability of being in any state is lambda over mu. This should actually be raised to the, so PowerPoint does its equations a little strange, but this is lambda over mu raised to the I times the probability of being in state 0. So if you wanted to know, if you could figure out what percentage of the time you're in state 0, you could then figure out what percentage of the time you are in any other state. And that's what we need. We need to know the percentage of the time we are in every state so we can then take a running average. So now the question is, can we figure out what is the probability of being in state 0? So since the probability of all the states all added up from 0 to infinity equals 100%, then we can sum them all up by having it lambda over mu raised to the I times p of 0, which then equals 1 over, this is from an infinite series, 1 over 1 minus lambda over mu times the probability of being in state 0. So if this all adds up to 1, and then I think I just wanted to rewrite this equation. So a lot of this is a repeat of the last slide, because it's just a continuation of that same thought. So just to recap, the probability of being in state 0 ends up being 1 minus 1 over lambda. This comes from this equaling 1. So if this equals 1, then P0 divided by 1 over lambda divided by mu should equal 1, which means that P equals 1 minus lambda over mu. So this result, the probability of being in state 0 equals 1 minus lambda over mu, is a result of the last equation, but it's also intuitive. What we talked about last class was we said lambda over mu was the utilization of the server, right? So we said that the percentage of time that the server is in use was equal to the rate into the system minus the rate at which things go out of the system. So just like an example, I think we went over last class, if the rate into the system was 1 per second, and the rate at which stuff can go out of the system, if this was being fully utilized, is 2 per second, then half the time the system's idle. So we said that lambda divided by mu was the percentage of time that the server was in use. And we're trying to figure out what is the percentage of time there are no customers in our system. That would be the percentage of time that it's not in use. So 1 minus the percentage of time it is in use will equal the percentage of time it's not in use. Does that make sense? So the result we figured out mathematically actually intuitively makes sense. The percentage of time this, let's say it's the CPU, is doing nothing is equal to 1 minus the percentage of time that it is doing something. So now for the MM1Q, we have a formula to figure out the percentage of time it's doing nothing. And if we know that, let me just go back, then we know the percentage of time that there is one customer in our server and nobody in the queue. We know the percentage of time there's one customer in our server plus 1 in the queue, which is state 2. And actually we could put any number here. And we could figure out the probability there's 10 customers in the queue. So it would be lambda over mu raised to the 10 times the probability we're in state 0. And the probability we're in state 0, we're now saying, is this. Okay, so now the expected number in the system when we arrive would be, now we know the formula for any given state. So it's the probability we're in state 0 times lambda over mu raised to the I for any number going off to infinity. So the expected number in our system would be, now do you guys remember how to calculate the expected number when you have a probability distribution? So like for example, an example maybe from a probability class would be a dice. So what is the expected value of rolling a dice? Do you remember how to calculate that? Because we want to use the same principle here. So what you'd end up doing is there's 6 faces on a dice, so they each have 1/6 chance of happening. So you would take the value times the probability it happens. So you'd say 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6. So you would take the value that the value of the outcome times the probability that outcome happens and add it all up. And that would be the expected value. So for a dice it would be 1 times 1/6 plus 2 times 1/6 plus 3 times 1/6 all the way up to 6 times 1/6. Add it all up, it would come to 3.5. So the expected value for a dice would be 3.5. And you're doing this, you're multiplying the value times the probability that it'll happen and add it all up. So if we want to know, this is like kind of our ultimate question at this queuing system. We arrive at the queuing system, we want to know on average, what do we expect? How many customers do we expect to be in front of us? Because we have to wait for them to be served, plus we have to be served. So to figure out how many customers are in front of us, the expected value is the number in front of us times the probability there will be that many in front of us. So that's I. Now the probability we're in state I would be the probability we're in state 0 times lambda over mu raised to whatever the I is. And then we just crank out the mathematics. Factor out any constants out of the summation sign. And what we end up doing is we end up factoring out one of these lambda over mu's, and then this ends up being an infinite series that we can equate to this number. So this, why is this infinite series equal to this? This kind of goes back to maybe calculus 2. But this ends up being a formula, and we can just kind of put this formula down on a sheet of formulas. So once again, the probability of being in state 0 is 1 minus the probability the server is in use. State 0 means nothing's in our system. And this ends up being the expected number we would see in front of us when we arrive. So now just rewriting some of these results, we have the probability of being in any particular state. And this is kind of a rewrite of the last one, the last slide. And this is the expected value of what we expect to see in front of us. Now, this formula, so yeah, the reason I rewrote this is because I just wanted to come to the last formula. We ran out of space on the last slide. So this 1 minus mu, and this denominator of 1 minus mu squared, we can just cancel this 1 and cancel this 2 up here. And then we end up with lambda over mu divided by 1 minus lambda over mu. So that's the expected number in front of us when we arrive. So here's an example of a queuing system. We arrive at a queue, so this is going to be an MM1 queue. This is an example of an MM1 queue. We arrive at a system. Now it's a system, our performance monitoring statistics have told us that arrivals are coming into the queue at a rate of 2 per second, and the service rate of the server is 3 per second. So just a reminder of what we said last class. It can spit out 3 per second, assuming it's constantly being used. But if it's only being used a percentage of the time, less will be going out. But this is the speed it could process, it could service the requests that are coming in. So we have a lambda and a mu, and now what we're trying to figure out is what is our total time in this queuing system. So we show one queue, we get served, and we're done. So our total time in the system will be the total amount of time we wait in the queue, plus then we finally get to the server and we get served. How long does it take us to get served? It would be the reciprocal of the service rate. So if the service rate is 3 per second, and we arrive and say, okay, I need service now, it should take 1/3 of a second, because it can serve at a rate of 3 per second, so each customer on average takes 1/3 of a second. So we want to know how much time we spend in the queue, plus how much time we spend being served ourselves. So how do we do that? We want to know the expected, so now we're going to look for averages. We want to know the expected number in the system times their service rates, which is 1 over mu, and then plus we have to be serviced, which is an additional 1 over mu. So how many are expected to be in front of us? We said from our last slide, it's lambda over mu divided by 1 minus lambda over mu. That's this part right here is the number of customers we expect to be in front of us. Each one of those takes 1 over mu to be served. Then we have to be served. So this is for us to be served. So in this case, we have lambda equals 2 per second and mu equals 3 per second. So the number of customers we expect to see in front of us is 2/3 times 1 minus 2/3 raised to the minus 1. So this is really going to be 2/3 divided by 1/3, which will be 2. So in this example, if we have a rate in of 2 per second and a service rate of 3 per second, when we arrive at this queue, we can expect, on average, for 2 customers to be in front of us. Could be 0, could be 1, could be 2, could be 3, could be 4, could be 20, but on average, we expect 2 customers to be in front of us. So the 2 customers that are expected to be in front of us will each take 1/3 of a second on average to be finished, to be processed. Because the processor can operate at a speed of 3 per second. So each customer will take, on average, 1/3 of a second. So we have 2 customers, each taking 1/3 of a second each. And now finally, we get to be served. And we take 1/3 of a second each. So our total visit to this queue would end up being 1 second. Where did the 1 second come from? The 2 customers in front of us took 1/3 of a second each, and then we took 1/3 of a second. So 1/3 plus 1/3 plus 1/3 is 1 full second. So we arrive at this queue with a rate of 2 in and a rate of 3 out. It'll take us a whole second to get through the queue. 2 seconds for the 2 customers we expect to see in front of us, 1 second for ourselves. So now suppose we had a queuing system like this. And this kind of goes back to what we went over last class, and like the first question on the homework assignment is like this. Our overall goal in this type of a question is, we're entering the queuing system. We want to know how long will it take from the moment we enter to the moment we're done. And if it's too slow, we have to use the operating system to manipulate how to make it faster, how to manage these queues quicker. So our goal is this. We want to know how many times will we enter this queue, how many times will we enter this queue, how many times will we enter this queue, and then for each one of those visits, how much time does each visit take, and then add that all up. That'll tell us how long from when we enter the system until we leave the system. So, and we kind of went over this last class, so just a little recap. We enter this system, and then 20% of the time we go to this disk drive. After we're done with this disk drive, we go back to the very beginning of the queue. 10% of the time we're on the processor, we get dispatched to the disk drive number 2. We get the page we need, a page comes in from a paging system, and it goes back to the queue and we start over again. 50% of the time, we time out. We just run on the processor and our time is up, so we go back to the beginning of the queue and we hit it for another visit. And 10% of the time, we finish and we leave. So the question is, for every time we come in here, how many visits to the CPU do we do? So last class we said that the expected number of visits, we'll use the letter E to represent that. The expected number of visits, E, was equal to, well, we're definitely, as soon as we enter the system, we know we're going to visit the processor at least once, the first time we enter. And then what percentage of the time do we go back to the beginning and start over? Well, 20% plus 10% plus 50%. 20, 30. Oh, this exiting should be, this should be 60%. It's got to add up to 100%. 20, 30, 60. Let's make this one 60. 60% of the time we go back to this queue, and 10% of the time we leave. So what that means is, for every time we visit the CPU, 90% of the time we take some action and then go right back to the beginning. And 10% of the time we leave. So the expected number of visits will be 1 for our first visit, plus 0.9% of the time we are going to revisit and rejoin the queue. So the equation would go E equals 1 plus 0.9 E. 0.9% of the time we will start over again. So if you subtract 0.9 E from both sides, you get 1/10 of E equals 1. And if you divide both sides by 1/10, you get E equals 1 divided by 1/10, so E equals 10. And you could review what we went over last class, if that doesn't make sense to you. But the idea is that for every time we come through here, we can expect an additional 9 visits back here, for a total of 10 visits. So every time we come in here, we're actually going to visit the CPU 10 times. So whatever the rate is into this system, you'll multiply that by 10, and that's actually the rate into this queue. 1/10 is coming from new customers, and 9/10 of what is in this queue is our repeat customers. Customers who came in earlier and haven't finished and keep repeating. Okay, so every time we come into here, there's 10 visits to this CPU. Now, what is the rate into this queue? Well, this queue is being fed solely by the output of this queue. So by inspection, we can just, what I mean by inspection, just looking at it with your eyes, we can see that whatever the rate into the CPU is, 20% of that goes into the upper disk drive. And whatever the rate into the CPU is, 10% of that goes into the lower disk drive. And whatever the rate into the CPU, we have 1/10 of that leaves. So we want to know, the things we need to know is, when we hit this queue, how long does it take to get from the beginning of the queue to the end? Multiply that by how many times we hit this queue. We need to know how much time do we spend getting through this queue, times how many times we visit that queue, and then add that to how long does it take to get through this queue, times how many times we visit that queue. So what we can do is then we can say, we have lambda, let's say in this example, lambda going into our system is 1 per second. So what that means is this: the rate along this line is 1 per second. But what we said was, every time we come along here, there's 9 additional visits coming in through these ones. So the rate into this queue is 10 per second. The rate into this queuing system is 1 per second, but the rate into this queue is 10 per second. So the rate into our overall system is 1 per second. The rate into the CPU component is equal to the expected number of visits to the CPU times 1 per second, which ends up being 10 per second. Then the rate into disk drive 1 is the expected visits to disk drive 1 times 1 second. The expected number of visits to disk drive 1 is 20% of this. So 20% of 10 per second is 2%. And disk drive 2 is 10% of the rate into the CPU, which is 1 per second. So what I'm saying there is this: if the number of visits into this queue is 10 per second, 20% of them go here, 10% of them go here. So the rate into this queue would be 20% of the rate into this queue. So if this is 10 per second, then they're coming into here at a rate of 2 per second. If this is 10 per second, then they're coming into this queue at a rate of 1 per second. So now we know what the rates are into all 3 queues. And the question gives the service speed. This one operates, the CPU operates at a speed of 20 per second. And disk drive 1 can operate at a speed of 3 per second, and disk drive 2 can operate at a speed of 2 per second. So with those, with the mu and the lambda of each of the 3 queues, assuming they're all MM1 queues, we can calculate how many customers we expect to be in front of us when we arrive. So the expected number in the system, the expected number in the CPU would be lambda divided by mu times 1 minus lambda divided by mu. So this ends up being 1/4 of a customer in front of us. And then disk 1 would be 2/3 times 1 minus 2/3 equals 2/9 of a customer in front of us. And disk 2 would end up being 1/2 times 1 minus 1/2, which is 1/4. So this is the number of customers we would expect to see in front of us. And then if we wanted to know the overall time before how long it takes to get through this entire system, it would be, we would add up for all servers, we would say the number of times visiting each of the servers, times the expected number of processes in that system, times their service time, plus one additional service time for us. And then add that whole summation up. And that would give us the overall time of getting from when we enter the system to when we leave the system on average. And then in this case, one of the questions we talked about last class was which device would get closest to 100% utilization first. So in this case, we have a rate of 10 in and a service rate of 20. So this is in operation 50% of the time. The rate into here would be 2 per second, but it can handle 3 per second. So this disk drive will be in use 2/3 of the time. And the rate into here is 1 per second, and it can handle at a speed of 2 per second. So this would be in use 50% of the time. So this device would end up being the bottleneck, meaning if we started pushing more processes into the system, we can handle it to a point, but once this disk drive hits 100% utilization, we wouldn't be able to push any more processes into our system because this queue would then grow off to infinity. And then processes couldn't get done. So that's basically the overall method. That's one method for doing this, but this is kind of the brute force. Just figure out how many times within your queuing system you want to have statistics for how many times you enter the system, and any time you enter a queue, is there a probability you'll turn around again and re-enter the system. And is there anything you could think of that would make modeling this as an MM1 queue is not realistic? Is there any, the MM1 queue makes those formulas we came up with earlier to predict how many customers will be in front of us on average. It made that math a little bit easier. But is there anything that's not realistic about that? It's not super unrealistic, but it's not quite realistic for operating systems. Yeah?
And the probability isn't that evenly distributed?
Yeah, so the MM1, it makes kind of the math easier. The idea of the MM1, so M stands for Markovian. What it basically means is we have an average, 1 per second, 2 per second, whatever the average is. We can always observe a system and figure out what the average is. But we're making the assumption that the gap of time between each of those events is totally random. And the other extreme from that is the deterministic case, where, like, let's say it happens 2 per second, and they happen at exactly every half a second. There's exactly one new arrival. That would be completely deterministic. And if they're averaging 2 per second, but totally random, that would be the Markovian way, the M way. So in a real operating system, for example, we're saying 60% of the time it runs and then times out. Well, the operating system almost definitely has a fixed time that it'll let it run, and then say your time's up. So like 60% of the time, the average is being determined by a clock. So that's not quite Markovian. And then when you go off to the disk drive, there's kind of a randomness. Sometimes you will arrive at an empty disk drive and you can get through quickly. Sometimes you'll arrive at one that's very cluttered. It'll take a long time. So the behavior of going to a disk drive on a pretty heavily loaded system, you're going to have an average time until the disk drive brings you a page in. There'll always be an average. You can just study the average over a period of a day. But how different they are from time to time could be highly varying, so that could be kind of Markovian, going out to something like a disk drive. But a CPU which stops out, gives it a certain time slice to a process, they're somewhat fixed in size. So they become kind of a hybrid of Markovian and deterministic. Then when we talk about other operating systems where the time slice that you get varies depending on your priority, then it does start to go back to being Markovian. So then this model starts to be a little bit more realistic.